तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the previous lecture, we are going into the details of the instruction cycle. That is an instruction cycle consisting of machine cycle and then in turn consisting of state, some low level activity I said. This state is nothing but the one defined by the clock period, the basic clock of a processor. Okay, so you can see that for each clock period, that is during each clock period, there is some minimum activity that is going on, that is in fact the state of the processor. Now that in fact sort of points to us that the study of a processor is essentially studying of a state machine in general. We will come to that a little later. Now how did we start? We said the overall computer system consists of the CPU, memory and I/O, and that interconnecting these we have the set of signal lines that is forming the bus. And now so far we had got an overview of the entire computing system and also something about each of these blocks, that is CPU, memory and I/O, and then I was telling you some information, okay, again an overall generalized information about each of it in detail. Now the time has come for us in fact to go into the details of each of these blocks. That is, in fact we had started with the CPU. Though we may identify each of these as CPU, memory etc., we cannot study them in isolation. Okay, some kind of interaction will be there, but first the focus will be on the CPU and then later on the memory, and in between we will also focus on the interaction. Fine. Now this is the design of the CPU, in fact is what we are going to take a look at, though not in detail, somewhat so that we will be able to understand what a processor is doing in the overall system. Okay, this is the main thing. Good. So towards the end of the previous lecture, that is what we started looking at. That is how we came to this instruction cycle. Now in this lecture as well as a few lectures to follow, we will be going into the details of a processor, what it is and so on. Now at least we know that a processor is a state machine. It is in fact a digital, an example of a digital system which is in fact a state machine, because it has to go through state after state as defined by the clock period, and then it will be executing its overall function. And what is the overall function? Essentially to execute instruction, mainly because the processor executes program and the program essentially consists of instructions and data. Okay, this we have talked about earlier too. Good. Now these instructions and data, they are stored in the memory. In other words, what we have is the stored program digital computer. That is what essentially it is. That is, the program is stored and the computer takes this particular program and keeps executing it. In this, essentially we have identified that instructions are the ones which tell what operations to be carried out, and then the data, that is on what operands, okay, the operations must be carried out. These are the two parts. Now this whole thing, instruction and data, they form the program, and that program is stored in the memory. Fine, good. Now that in fact points to what we know as von Neumann architecture, okay, because it was a mathematician by name John von Neumann who had thought of this particular thing, that is storing the program in the memory and executing them. In fact, this is a German name, so you have to pronounce as von Neumann. And even today, for instance, 90 to 95% of the computing systems, they are based on this architecture, that is von Neumann architecture, in which we have a memory in which the program is stored and that is executed. Later on we will also talk about a few other architectures which have sort of been derived from this particular main thing. Okay? Though this course, the series of lectures is not on architecture, it will be interesting for us to know some details about this too. Okay? Fine. Now let us go back. The program consisting of instruction and data, and the program is executed for what purpose? For something. Some data will have to be processed and the results must have to be delivered, right? So instruction after instruction the program is executed, and that means the processor is going through series of instruction cycles. What it does is fetching the instruction and executing the instruction. And I already mentioned that in the execution of the instruction there will also be data fetch. Data fetch or instruction fetch will be similar because both are stored in the memory. So in this execute phase you may have data fetch also. Why? It's like this. We said the program is stored in the memory and the data also stored in the memory, and so the CPU fetches an instruction, or when it fetches the data, let us say, both the time it is behaving in a similar way. The CPU will address the instruction, what address? A location which contains the instruction. Similarly, the CPU later on may address a location which contains the data. Okay. So when CPU addresses memory and the memory responds, this is what we are talking about. So in one case, that is during instruction fetch case, the memory will be responding with an instruction, and if there is a need for fetching the data or the operand which will take place during the execute phase, then the memory will place the address of data or the operand and the memory will respond. Okay, the CPU will address that particular location which contains the data. Good. So each time whenever the CPU accesses the bus and makes a demand, then we said there is a machine cycle. Okay, whenever there is a bus activity, what is a bus activity? Bus activity is essentially for fetching an instruction or fetching some data, and both are stored in the memory, right? So whenever CPU accesses the bus for fetching instruction or for fetching data, there is a machine cycle. Good? Fine. And during the machine cycle, the processor goes through a series of states. Now as shown here, this fetch phase of the instruction cycle consists of 1, 2, 3 machine cycles, which means essentially the processor for fetching this instruction makes use of the bus 3 times. That is, from 3 memory locations it is fetching the instruction. Okay? And as shown here, for example, this particular first machine cycle consists of 2 states. Okay, 2 states, that is basically the processor is going to make use of 2 clock periods, 2 clocks, that is 2 basic activities. And what these are, we will see that in detail later. For doing this particular thing, we say the processor enters state 1 and then it enters state 2. So essentially the CPU can be looked at as a state machine, okay, as a state machine. That is, it is going through a series of states. That's what we talk about. Now that in fact is the basic concept of any digital system, right? What is it? Processor, CPU. It's an example of a digital system. So good, we'll talk about this more. Now next, I said about the von Neumann architecture. That means we are considering memory as a single block in which both the instructions and data are there. Now later on we will see how this memory can be split into different blocks, and then different architectures also will keep following. Fine. Now when it comes to the state machine, that is where some basic activity is going on, okay? It may be as simple as moving contents from one place to another place within the CPU. Now what is these various places within CPU? At least we got some idea about the memory last time. I said the memory may be organized so that let's say that is the memory. I said it may be organized so that it consists of some locations and each of which can be uniquely addressed, okay? So there is some unit of say data that is there. Normally the memory stores, we will be using a general term that's called a word. Memory stores a word, right? The word may consist of a sequence of binary digits, zeros and ones, that is a string of zeros and ones, okay? But be careful whenever you come across the term word. It is sometimes word is taken as some specific width, okay? But it's also the term word is also used in a very general sense, okay? So for instance we can talk about what is a binary digit is a bit. Now for instance we may talk about a 4-bit word, 8-bit word, 16-bit word, 32-bit word. In that sense word is. Otherwise normally word would mean a 16-bit word. This is also there. So be careful. Now whatever be the length, okay, let's say n bits, right? So each location holds an n bit word. Good. Now similarly in the case of the CPU, since this information that is a unit of information or data comes over the bus, will it not be meaningful for you to assume that if this is n bit in width, it's also meaningful for the bus also to be n bit, and then CPU also has some internal storage facility, again each of with n bit. It's meaningful, no? Though not always it need be true, but it's meaningful. Then we talk about matching. That is the CPU which can hold an n bit word, okay? That's what we say is whatever n is, n bit word, and remember I am using the word in a very general sense, n bit word. The memory holds an n bit word and the bus can transfer the n bit word and the CPU can receive internally, that is the CPU can receive internally this n bit word, okay? So the element which stores such unit of data in CPU, generally it is called a register, okay? A register. Fine, but it's not, it need not always be true. One need not have an n bit CPU and then n bit wide memory and n bit wide bus. It's not always necessary, but it's meaningful. We'll assume it that way. Incidentally, why don't I point out something? Now, there are two ways in which I can diagrammatically represent parallel lines. Now, for instance, n means n parallel lines. Now, for here, the way I have marked, okay, with two things. Now, there is, I'll use another term, another character. I will say m, which means basically there are m set of signal lines here. Okay, this is one way of representing. Another thing is just put one thing and then have a slash there and then write M, which means this particular thing is M. Okay. So there are two ways in which I can write. Either I can have a parallel line like this and then indicate M, or instead both are identical. Put a thing like this and write M. Both are just the same. Okay. Now that also let us note down. So it will be meaningful to see that the bus width, the memory word width and the CPU word width, they are all matching. Okay, they are all same. It's meaningful, but remember it need not really be so all the time, but it's meaningful. Okay, now let's come back to this register. So the CPU holds some data in the register. Now as long as the CPU holds a data, the CPU need not address the memory and get that, it's available internally. If the CPU does not have the data in itself, then only it need to access the memory. So when we say that this particular thing consists of two, or rather here 3 machine cycles, basically we are saying 3 times the CPU is accessing the bus. Now let's assume that as part of execute phase you have an operand fetch, that's the data fetch, right? Suppose the data that need to be fetched from the memory happens to be a 2 word, then during data fetch there will be 2 machine cycles. Now on the other hand, if the instruction that is fetched points to a data which is already available in the register in the CPU, in that case the CPU need not access the bus, the data is already available here. So CPU always accesses and gets what it does not have. Since the instructions are always stored in the memory, it need to fetch. So data sometimes may be available with the processor, in which case it need not make use of the bus. That means there won't be any machine cycle. Okay? Only when it does not have that, then it will access. Good. Now the CPU must have the instruction, that is fetch the instruction, and it must fetch or have all the data that is required. Then after that the execute phase starts, which means basically whatever that particular instruction says, the corresponding operation will be executed. Okay? So if the instruction is an add instruction, the operation of addition will take place after it has got, say, both the numbers. Suppose you have an instruction like add AB, right? Then once the CPU has A and B, whether A and B are fetched from the memory or they are locally available from CPU, whatever it is, right? Once it has these 2 data AB, then addition operation will be executed. So in other words, what's happening is the instruction must be fetched. This in fact we have talked about earlier too. Instruction must be fetched, and then what that particular instruction is, it must be interpreted or decoded, and then that particular instruction must be executed. Okay, that is instruction fetch, decode, execute. Now these are the 3 things that take place during an instruction cycle. Then the particular one instruction in a given program is executed. So like this the processor keeps doing one after another, right? This is the way a program is executed. Now whatever may be the application, finally there is going to be a program, and that program is going to be executed by the processor in this particular manner. Fetch the instruction, decode the instruction, execute the instruction. So what happens is, first the instruction is fetched, and that itself will be in a coded form. Okay, essentially what that particular thing will be like this. What we are talking about here is the instruction format, meaning the way in which the instruction is organized. Okay, this instruction format, it will be some words length. Now one part of it will be the opcode, the other part of it will be referring to the operand or the data. Okay, the other part of it will be. So this opcode is the one which will be decoded, and the operands once fetched from the memory will be executed as per this particular operation. So an instruction format essentially consists of opcode and operand, which means essentially after an instruction is fetched, the decoding will be starting from the opcode side. That's where you have to decode, and depending on the instruction, it will also indicate how many operands. Sometimes there are some instructions in which no operands are referred to at all. It's possible. We were talking about addition. Addition means implies at least two operands. So we talk about a double operand instruction. That is, addition is one such. Okay, double operand instruction. Then there may be instructions in which there is only one operand, single operand. Okay, single operand. That is, for instance, supposing it says just change the sign of the data, right? Now it's nothing. Okay, just take one data and then change its sign. It's only one single operand. Another thing, like for instance, the register contains some data, and there can be an instruction which says clear that register. Clear that register is only one thing, right? The same thing, clear one location. So if you are just referring to only one unit, then it's going to refer to only one particular operand. So that operand which contains, the location which contains that particular operand or the data must be cleared, single operand. And in something in which no operand will be, or zero operand will be same, no operand even will be referred to, right? Or there is no need for explicitly stating what the operand is. For instance, you have simply halt the processor. Where is the operand? Absolutely no operand involved. Halt the processor. Okay. So the instruction format, which generally must take care of reference to at least two operands. Okay, there can be multiple, but they have not been. There are processors which take care of even more than two operands. But of late, generally we have only this double operand, single operand, or no operand instructions. Good. So while decoding this opcode, the processor will know which type of instruction it is, whether it's double operand, single operand, or no operand. Then it will look into the other part, and then it knows what it is. Okay, no operand means there won't be any reference to operand at all. So for instance, if add is the instruction, minimum it's double operand. So then it will fetch the two operand. So once it has the two operands in, then it will carry out that particular instruction. Now similarly, other things too. Good. Here, what is important is, yes, we will not go into the details of this instruction set or how an instruction is executed. There is something more we need to note down here. I said it is meaningful if the width of memory, the width of register, and the width of some part of the bus, they all match. That is, the data part of the bus, they match. Good. And I also said they need not match. What do I mean by that? Now I'll try to introduce a few things. Suppose we talk about an 8-bit CPU. Okay, that is bit standing for binary digit. Or when I talk about a 16-bit CPU. Okay, what is it I'm actually referring to? Then what about the memory? Again, memory also I have to talk about the width. I'll come to it a little later. An 8-bit CPU basically means the data that can be handled by the CPU is of 8-bit. That is, data being handled, I would put it as being processed by CPU is of width 8 bits. Okay, that's what it means. In the case of 16, it is 16 bits. When I say data being processed by CPU, what we are talking about is what the processor would be doing internally. Okay, what the processor will be doing internally. So we would say data being internally processed. Okay. Because a processor may be capable of processing a 16-bit data, but the memory may supply only an 8-bit, in which case the memory must do it twice. That is, memory must supply the data twice, 2 8 bits. And it's now the width of the bus also comes. Now specifically what we are talking about is the data width of the bus. Okay, the width of the data part of the bus. That's what essentially we are concerned in this particular thing. Okay. Now the memory generally these days is organized so that the width of the memory is 8. Okay, n equals 8, meaning 8 bits stands for what is known as byte. So when a memory is organized so that the width of the memory is memory word is a byte, then that is the memory I am talking about. Then we talk about a byte organized memory. Now why do we organize memory in this particular way? Now 8 is a very convenient figure. Then in case of more than 8, then we talk about multiples of 8 bits. That's what it is. That is 1 byte, 2 bytes, 3 bytes, 4 bytes. So that 8 bit, 16 bit, or generally we go for 32 bit, 24 bit is also possible, but 32 bits, so on. So multiples. Maybe in an application, the data that is referred to in one case may be an 8 bit data. Maybe for some other thing in the same program we may be referring to the double the size of that. So we may also deal with 16-bit data. Okay, but generally less than 8 these days we do not bother, but it's possible to organize if one wants it. Good. So generally what we have these days is a byte organized memory, in which case the memory is going to hold the data in units of bytes, and similarly the bus, okay, generally it will be capable of transferring an 8-bit or 16-bit or 32-bit data, and CPU also an 8-bit CPU or 16-bit CPU or a 32-bit CPU, like that. Now let's now we need not worry very much about the memory because it's byte organized. The bus, what is the bus width and what is the CPU size? So I said an 8-bit CPU means the data being internally processed by CPU is of width 8. That's what I said. Okay, in other words, we are not talking about the width of the bus or the way the data is organized. What we are talking about is the internal processing capability of the CPU. In other words, what did I say earlier? What is processing essentially consisting of? Either it is arithmetic or logical, right? That's what it is. So I had said earlier, recall, arithmetic processing will be carried out or logical processing will be carried out, and that for carrying out this we have the arithmetic logic unit or ALU, right? Essentially when we say 8-bit CPU, what we mean is 8-bit ALU. When we say 16-bit CPU, what imply is 16-bit ALU. It does not tell about anything, the memory or the bus or something else also. We will talk about that a little later. Okay? So, essentially the internal processing by the processor is carried out with ALU as the main thing, and we talk about that particular width. Having seen that ALU of a particular width defines the CPU of the same width, right? What is this ALU? It said arithmetic and logic processing, and the processing is going on data. So, essentially the CPU will consist of some paths or routes, okay, over which the data will be routed. That is what we talk about is, given the two data, how this particular data must move over, okay, that is the path which defines the path the data will be taking over. And then the other part of it is this particular movement of the data over a certain path, in what sequence, in what time sequence this must be going on. That is, in other words, again we talk about data path. So, I will just put it as data path. Specifically, this is the one which talks about the control aspects. That is, data path and the data path control. These are the two aspects of the circuit which constitute the CPU. So, essentially CPU design boils down to design of data paths and the design of the control. The control is nothing but the controller which is going to sort of orchestrate the movement of the data over these paths. Then for one particular instruction there will be one path and one set of control signals. For another instruction it will be a different path, maybe even same path, and different control signals certainly. Okay. So, essentially the CPU design boils down to data path, which in fact we may just put it as arithmetic logic, okay, circuitry, okay, that is arithmetic logic circuits, and then we talk about the control circuits here. So, this is what the design of a CPU will be. Good. Now, let us go back. This data processed based on a given instruction. That means we have to go back to that instruction cycle consisting of machine cycle, each machine cycle consisting of state. In other words, this particular CPU design is nothing but a digital system design, an example of a digital system design, okay, which means CPU as a state machine. So, we have to develop some idea about the state machine concept. You have to have some concepts about that. Now, what is it? In each state or the clock period, okay, the CPU enters one state and it carries out some basic activity. Recall, right? That is instruction consisting of machine cycle consisting of state, and in each state some basic activity was going on, and that basic activity is on the data. And within the CPU, what do we have? Essentially we have registers, right? So, the basic activity which will be going on during a state, since essentially it goes at the register level, because we are talking about within the CPU, because it takes place at the register level, this basic activity can be considered as register transfer activity, okay, register to register some transfer or clearing a register and so on. At the register level we are talking about this. So, this will be generally called a register transfer level activity, or just simply as RTL, okay. And in fact we have a language which explains the sequence in which the data is moved, for which the different registers in the CPU will be made use of. So that once you state will describe the whole behavior of the CPU or the processor, right. So a register transfer level activity, at this level the CPU is going to do, and the design of a CPU will consisting of design of data path circuit and the design of the control circuit, and the entire behavior will be at the basic level, that is the RTL level. That is what it is. Now let us develop some concept of the state machine before we proceed to take a look at the RTL. For the present, note that at the state, that is during one clock period, this is what is going on. Fine. A state can be represented, let us say, using a box. Okay, the machine enters a particular state. I'll just call state A, and in that state it generates some output which I will enter. So I'll just name that particular signal as out1, and in the same state A it checks for some input. Okay, so I'll just call name that signal as inp1 or something, and depending on the state of that input being, let's say, 0 or 1, or the logic state being false or true, then the machine may enter another state, okay, like this. The other state, or we may call as a next state, as B, or the other one as C. What we say is, for the present state A, the machine, what we are talking about is a state machine. For the present state A, the machine generates an output 1, and in that state it checks for an input, and depending on that particular input being false or true, the next state, the false next state is B, and the true next state is C. And again, in the next state we talk about, as we did here, what is the output and what inputs it checks, and so on, so forth. Now this is a simple picture of a state machine. So this is what precisely the processor is doing. The processor enters during the instruction cycle one state. In that particular state it generates some signal, okay, and it also looks for some input signal, and then it decides on the next state. Now shown this way, it may appear to you as if in any one state only one input can be generated, can be checked, or only one output can be generated. Not necessary. There can be more than one output, and here also there can be more than one input checked. It's possible. All right, it's possible to do that, but this is one simple way of looking at it. That is in which which will help us develop some concept about the state machine, right. So let us not discount the other possibility of having more than one inputs to be checked and having more than one output to be generated. Good. So you can now see that a computing system essentially revolves around the processor, and the processor as a state machine finally just is going through state by state as per some algorithm, and that particular thing, in each state it is going to check for an input and it will generate output. In other words, the whole system design will boil down to two things. What is it? One is output function generation, okay, output function generation, and second is the next state function, correct? The next state function. That means the processor to start with enters a state, we will call it as initial state, and in that initial state the output function will tell what is the output to be generated, and in that particular state the next state function will tell what is the input to be checked, and depending on the condition of the input what is the next state is. So the design of a processor is essentially arriving at these two functions. Okay, good. Now let's try to see what exactly, for instance, is the output and input with reference to our CPU. We need to know that, right? Let's go back and see what was the processor doing. The processor first in its instruction cycle will take a machine cycle. Okay, the next one. We have seen what is taking place during a state. It is in every state it is going to involve in some RTL activity, something. Well, if you have not got a right picture of what exactly the register transfer, you will come to that later. It's some basic activity and it is the lowest level. So we will go to the next level. What is that machine cycle? What is the CPU doing? First, the CPU addresses memory, we said, right? And we'll assume an instruction fetch, in which case what the CPU doing is, the CPU is placing the address of the instruction on the bus. That is what it means. CPU places the address of the instruction on the bus in the case of instruction fetch. Now the memory must know whether it must accept, because memory is always a slave, does it know? The memory must know whether it must accept something coming into it or it must generate how it should respond. The CPU must also indicate that particular thing. So CPU generates I'll say in general the control signal. Okay, what is that control signal? Now in the case of instruction fetch, it's essentially that the memory must send the instruction. Okay, that is with reference to CPU, we talk about the instruction word which is coming over the bus as a data, right? Now remember, I was telling you once, when I say data, don't confuse program construct instruction and data. From memory point of view, whatever that is stored is a piece of data, some unit of data. Now in the instruction fetch, the memory must respond with the instruction word. Now that comes as data over the bus, which the CPU will read. So the appropriate control signal in the case of instruction fetch will be read. Okay, that will be the control signal. That is, the CPU says, CPU tells the memory, let me read the content of this address, which is an instruction. That's what it is. So CPU places the address of the instruction on the bus and CPU generates the read signal in the case of instruction fetch. Okay, in some other thing it may be a write. So that's why I use the word control. But if CPU wants something to be written into the memory, what is the implication? The CPU must not only address, but it must also place the data. Then only that data can be written into the memory. Okay, we will come to it later. I thought in passing I will mention that too. Now the CPU addresses the memory, the CPU generates the read signal. Now as a true slave, memory must respond and memory must place the data on the bus, so that the CPU may read this data. And in the case of instruction fetch, what is this data? Okay, in the case of instruction fetch, which is the first thing in any instruction cycle, okay, in the case of instruction fetch, this data is nothing but one instruction. And remember here, we don't know about the size of the instruction. The instruction may be an 1 byte instruction, or a 2 byte instruction, or a 3 byte instruction. So assuming it is 1 byte instruction, the CPU will place the address of that byte, it will get that byte, that is what it means. Now if it happens to be a 3 byte instruction, the CPU must place the 3 addresses one after another, that is what it means. Okay, good. So let us remember that all the time, because we talked about the width of the memory, width of the bus, width of the CPU, and then in general when we talk, we must always correlate, okay, because the instruction size can vary. Good. So now CPU addresses the memory, CPU generates read signal, and memory places the data on the bus, I said. Now obviously the next step will be CPU reads in the in this case instruction, right, because I said instruction fetch, but in general this is nothing but a data which the memory has responded with. Okay, this instruction, what is it? Essentially it's nothing but a data which has come, or rather which has been placed by memory in response to CPU's requests, right? We just assume that we are discussing instruction fetch. That's why we are talking about an instruction which the CPU reads. Now let's get back to our basic concept. What is that? CPU addresses the memory. So the CPU must place the address on the bus. So now this I will try to translate into this. CPU addressing the memory, this particular thing I will rewrite as some address is placed by the CPU on the bus. Okay, some address is placed by the CPU on the bus. Now CPU generates the control signal. I will assume read. So I will say some control signal, call it read, is placed on the bus. All these are put in different parts of the bus. We will come to that later. Then memory places the data on the bus. Okay, so I just put it as memory, okay, data, that is memory part does it. This goes on the bus. Now here it's all CPU doing that. Now CPU reads in the instruction, which means whatever was there on the bus, that is actually the data. The data what was available on the bus is going into the CPU. Okay, so in the CPU means I will just put it as it's going into some register. Okay, now we have assumed that it is an instruction, so it's not it's okay on my part to assume that this particular thing goes into what I may call it as an instruction register. Now do you see the register transfer activity? Some part of the bus is going into a register. This is the basic activity. Similarly, the CPU placing the address. Now this may come from an address register of the CPU. Okay. some address register of the CPU, it goes into the bus. It is just transferred. And then here this is a control signal actually. So this is in fact a read signal, doesn't matter. The read signal is placed on some part of the bus. Here again a simple transfer. And then here the memory contents, that is data, is placed on the bus. That is, the contents of a memory location is transferred onto some part of the bus. Agreed? So now you must have got a nice concept about what we mean by register transfer, and that is precisely what is taking place in each state. So the processor must go into one state, do this, and then it must go into another state, do that, and so on and so forth. Well, where are these inputs coming from? We will have to wait. Maybe in the next lecture we will talk about that too.